Okay, so today I'm going to kind of talk a bit about some of one particular piece of kind of very Ethereum 2.0 relevant technology that and I've been working on along with some other people have been working on over the last couple of years, which is data availability checking and fraud proofs and how to use these things to improve scalability. So start off by talking about the problem, right? So first of all, blockchains are increasing in capacity. Even the Ethereum blockchain just increased its gas limit from 8 million to 10 million about 1 month ago. The chain's capacity increased by about 25%. And guess what? Before the capacity increase, the chain was full. After the capacity increase, the chain was still full. So there's a lot of demand, right? Lots of people love Ethereum and wants to use Ethereum. After the Istanbul fork, the data capacity of the blockchain is, so not the computation capacity, but the data capacity will increase by another factor of 4. And you can guess that the Ethereum blocks will get even bigger and the chain will still be full. And there are other blockchains, and so there's the chain of our good friend Craig Wright that goes up to a bit under 1 million bytes a second. And with ETH2, of course, we plan to be even more ambitious, and we plan to go up into kind of the several megabyte per second range. So when you have blockchains that have a very high capacity, then you get a problem, which is that individual computers are not powerful enough, do not have enough bandwidth, do not have enough computation, do not have enough of everything to be able to actually fully verify all of this data, right? Another challenge is quick verification of history. Who here has synced an Ethereum full node in the last month? Why are there not more hands? What about who here has synced an Ethereum full node in the last year? Okay, so some people, but not everyone, right? So why not? Basically because there's a lot of data. The Ethereum blockchain is over about 100 gigabytes. The state is now about 50 gigabytes. Thanks to some really heroic engineering by the Geth team, also by the Nethermind team and other people, it's syncing an ETH client actually continues to be a pretty tolerable experience. So I synced Nethermind about 3 weeks ago, and it managed to get the entire state in about 12 hours. And 2 years ago, when I did synced all the nodes, it took maybe about 4 or 5 hours. So even despite huge increases in engineering efficiency, it's clients are still taking longer to sync, right? And so we want to ideally have some mechanism to kind of verify years of history, but also not just get the state, but also actually verify that the history of the blockchain is correct, right? You want to verify that the coin supply hasn't been tampered with, that your favorite smart contract hasn't been illegally tampered with, unless there was a hard fork where everyone agreed to it. So it would be nice if we could actually verify that everything that happened in the past is valid, without actually checking everything in the past, because that's called an archive node, and that now takes over a month. So what's the goal here, right? So basically, indirect validation. So in kind of many parts of the crypto space, there is this kind of religion that says that to be a real citizen of a blockchain, you have to basically verify everything yourself, right? You have to be a full node, you have to sync the entire chain, personally process every transaction, personally verify that every transaction is valid. And there's good reasons behind this. It creates a kind of very strong force that makes it very difficult for even colluding miners and 51% attackers to add changes into the blockchain that create invalid state transitions. So if you do a 51% attack, you can revert some transactions, but you can't actually create more coins than there are supposed to be coins. You can't steal other people's coins. You can't give yourself free coins. And full validation basically kind of gives us this, right? Because a chain that does any of these invalid things is just kind of by definition invalid and nobody accepts it. The problem is full validation does not scale. And so the goal here is, can we get most of the benefits of full validation without actually doing full validation? And the approach is indirect validation. So basically, you come up with mechanisms where the set of kind of client nodes together kind of somehow collaboratively verify blocks. I verify a little piece, you verify a little piece, someone else verifies a little piece, and together we verify everything. And ideally, we want a mechanism that is not honest majority dependent, right? That continues to work even if there are 51% attacks. So the ETH2 sharded design, for example, right now it's very heavily dependent on committees. So basically, you randomly select some small number of nodes to verify this thing, you randomly select some small number of validators to verify that thing. But committees definitely are kind of honest majority or rational majority dependent, and if there is either a global 51% attack or some kind of highly targeted attack on one committee, then the committee mechanism by itself doesn't protect you. And so we want to have a mechanism that does protect you. So if it's not honest majority dependent, then what security models are we okay with? One example is fraud proofs, right? So fraud proofs basically say, well, you come up with a mechanism where there is computation that's being run, but by default, not everyone runs it. Instead, you have a few people run it, and if any one of them discovers an error, then they can publish a proof of the error, broadcast a proof of the error, and everyone else, once they see this fraud proof, know that this piece of computation actually is not actually correct. Right? So this is a kind of collaborative validation. And fraud proofs require a one-event honesty assumption. You need at least one honest participant and subjective network synchrony. So if network latency is too long, then you're not going to receive the fraud proof. Another one is data availability sampling that I'll talk about today. And this one, instead of requiring one honest client, it requires a somewhat higher number of honest clients. Could be 500, could be 1,000, somewhere around that range. But it's not a 51% honest or even a 10% honest assumption, right? It can handle any number of dishonest clients as long as there are enough honest ones. So fraud proofs. So let's talk about fraud proofs. So here's the kind of basic model here. You have a malicious miner or a malicious validator publishes a block. And let's say there's a 51% attack happening, right? So they get away with it. The longest chain now contains invalid blocks. All of the block data is present, but some of the block data might be invalid. And so the goal here is basically to try to kind of design the protocol so that no matter how the data is invalid, if the data is invalid, there's some specific piece that needs to, that's got to be the kind of the first piece that is invalid. No matter what it is, you can make a reasonably short proof, a reasonably short kind of set of Merkle branches, sort of set of portions of the state that can be authenticated with hashes, and you can use this to prove that, wait, something inconsistent happened over here. So you need a full client to create one of these proofs, but once one of these proofs is created, the proof can be broadcasted, and another client can download a proof, they can verify the proof, and it works, right? So if they verify the proof, they realize the block is invalid. Now, fraud proofs, even by themselves, they have one huge weakness, which is, what if data is missing, right? So what if a block may be correct, maybe is incorrect, but you can't tell because the entire block data has not been published. Maybe only the header and 3/4 of the block have been published. The block could be invalid, but because you don't know what the rest of the data is, you can't really tell whether or not the block is invalid. Now you could have someone notice that that particular part of the block is invalid, and then they publish a message saying, hey, look over here, I can't find this data. But then this is attackable, right? Because if someone publishes this kind of message, then whoever published that block can just publish that little piece of data. And then you raise the alarm on another piece, the publisher of a block can just publish that data. And so basically, if you try to use a fraud proof-like mechanism to verify availability, you just create a denial of service attack, and everyone ends up having to download everything. Now, this isn't always a problem, right? So for example, let's say you have an environment that's very computationally constrained, but not data constrained, such as you're running a Python client. So if you're running a Python client, then what you can do is you can just download every block. And downloading every block is still just as cheap as it was before, but computation is expensive, and so you don't actually do the computation until you get sent a fraud proof. And if you do this, then the benefit that you get is basically that kind of conditional on the security model of a fraud proof, which says that messages kind of fly around the network and fast enough that if there is something wrong, you'll find out about it. You basically get the benefits of full validation without having to pay the cost of doing full validation yourself, which, if you have a Python client, like, are extremely high, right? Python like literally takes longer than the block time to process blocks in many cases. So fraud proofs by themselves are useful. Optimistic rollup is dependent on fraud proofs, and optimistic rollup can achieve scalability of up to like a few thousand transactions a second, even on the current Ethereum chain, but they have a limitation. So data unavailability attacks, right? So the block header is present, but some or all of the data is still missing. So we can think of the data unavailability problem as a kind of separate problem to the catching fraud problem, right? So the problem here basically is, suppose you have a block, and your job right now is you don't care about fraud, you just want to prove that some particular Merkle root represents a piece of data where all of that data actually is available. All of that data actually is kind of floating around the network, and for every chunk of data, that chunk is held by at least one honest node somewhere. And so if for any specific piece of data you were to ask for it, you could get it. So the question is, how do you verify availability, right? The trivial way to verify availability is to download everything yourself. But the problem is that we're talking about blockchains that are processing multiple megabytes a second, and despite what internet service providers advertise, internet connections are not going to be fast enough for many people to actually continuously download all of this data every day. So how do you verify that data is available without downloading it? So let's consider one kind of strawman protocol, right? You have your Merkle root, you have your little hash that's at the root of a Merkle tree, and instead of trying to download all the data, you're going to just select 80 random positions, you're going to select 80 random indices in the tree, and you're just going to ask the network, hey network, I want to learn a proof that shows me what is chunk number 74. Hey network, I want to learn what is chunk number 235. Hey network, I want to learn what is chunk number 612. Whatever set of indices you choose, you only accept the block when all of those indices have been responded to, right? So you pick a set of indices and you wait until you get proofs for all of those indices, and when you get proofs for all of those indices, then you accept that the data is there. So a big problem with this is that it does a good job of proving that more than half the data is available, because if less than half the data is available, then with extremely high probability, any particular node's check is going to fail. You ask for data, and at least one piece of data is going to turn out to be not available. But what if 90% of the data is available, right? So maybe 90 or even 99%, but not 100%. What if, in the worst case, only one piece of data in a block is missing, but maybe that one piece of data is very important. Maybe that one piece of data is a transaction, and you have a block claiming that that one transaction withdraws 500,000 Ether from the Ethereum Foundation wallet. So this kind of scheme can prove that half the data is available, but because it uses random sampling, it cannot cover the case where 99% of the data is available, where only one chunk is missing. So how do we handle this? Erasure coding. So basically, suppose there exist these mathematical protocols where you can take a piece of data that has some number of chunks, so it has n chunks, and you can extend it to 2n chunks such that any n of those 2n chunks can be used to reconstruct the whole thing, and from there reconstruct the original data. So you kind of, this is basically done by kind of pretending that the original data is a set of evaluations of a polynomial. You figure out what the polynomial is, you evaluate the polynomial at a bunch of other points, and like if you have enough evaluations, you can reconstruct what the polynomial is, regardless of like what specific evaluations you have. But like regardless of kind of the lower level details of the math, what matters here is that if you do this, if you kind of do this sort of low degree extension of some piece of data D to a piece of data D prime that contains D but also contains some other data, then any 50% of the bigger data D prime is sufficient to reconstruct the whole thing, and so it's sufficient to reconstruct D. And so what erasure coding does here is it basically means that we've converted the verify 100% availability problem into a verify 50% availability problem, right? If you publish a root and less than half the data is available, then anyone who does one of these random sample checks, anyone who does this kind of trick of asking random Merkle branches, some of those checks are going to fail. With extremely high probability, if less than half the data is available, then at least 1 out of 80 checks is going to fail. If more than half the data is available, so if almost all the data is available, then because of how erasure coding works, the rest of the data can just be reconstructed. So if we can do this, then this basically by itself kind of gives us a protocol that we can use to verify that data is available without actually having to download all of it. Now, there's a problem with this, right? And the problem is basically that what if the erasure code is not constructed correctly, right? So what if instead of kind of correctly encoding, treating the data as a polynomial, figuring out like where the evaluations are at other positions, what if instead at some of the other positions, the data is just random junk, right? What if the hash is kind of just malformed in some way? What if there isn't even data in some position? Now, the good news is that there is a fraud proof for this, right? So if someone creates a block where the erasure code is not constructed correctly, then the fraud proof is pretty trivial. If more than 50% of the data actually is available, then you can just locally reconstruct the rest of the data, and you can locally figure out what the Merkle root should be. And if the Merkle root that should be is different from the Merkle root that is, then you can see that the block is fraudulent, and you can just broadcast the entire block as a proof that the entire block is bad. So this is kind of trivial, right? But the problem is that this is too big. Basically, one of these entire blocks, like it really could be huge. It could be potentially many megabytes, could be even more. And like we want fraud proofs to be reasonably sized, because if a fraud proof is not reasonably sized, then, well, how would we even, like, you can't put it into a blockchain and use it inside of a blockchain protocol to take away someone's deposit, for example, right? Or even just clients can't even download it. So what do we do? There's a couple of different approaches here. This is an approach from myself and Mustafa about 2 years ago. And basically the trick here is instead of using a one-dimensional polynomial, we use a two-dimensional polynomial. And so instead of a fraud proof having to contain the entire data, like basically the fraud proof only has to contain one particular row or one particular column of an extended square. And we can see some statistics here. So for example, if you have a gigabyte of data, then the amount of data that you have to download for to verify availability of the whole data is only somewhere on the order of about 200 kilobytes. And the size of a fraud proof is also somewhere around 200 kilobytes. So downloading 200 kilobytes to prove availability of a gigabyte, it's pretty good, but it's still not perfect, right? But so this is one solution. And there's also this really interesting paper that literally got released about a week ago. And the paper uses a different kind of erasure coding scheme. And it also does this clever trick where instead of just erasure coding the bottom layer, you kind of erasure code every layer of the Merkle tree. And it has some serious trade-offs. So for example, for this to work, you need to verify that more than 7/8 of the data is available. And so the amount of data you have to download to make these random checks has to be significantly higher. But the good news is that a fraud proof is very tiny. So these are kind of two kinds of improved protocols that both do similar things, and they both kind of depend on fraud proofs, right? So here, basically, if you use either of these techniques, then you can verify that some really big block is valid and available using just a header if you download a bit of extra data and you kind of combine these sampling checks with fraud proofs of data is incorrect, and you have this kind of indirect verification of a block that gives you kind of equivalent properties to fully verifying the block yourself, conditional on a couple of extra security assumptions that basically say, number one, the network is fast enough that fraud proofs get broadcasted, and number two, there are at least some minimal number of honest clients, so maybe at least 500 honest clients somewhere else in the network with you. A third approach is to bring in Starks, right? Who here has heard of Starks? Who here has heard of Snarks? Okay. So basically, what a snark or a Stark is it's this general purpose zero-knowledge proof. So it's this kind of cryptographic proof that you can generate. And what this cryptographic proof does is it lets you basically say, I ran a computation on this piece of data, and this proof verifies that here is the output of this computation, and this computation was all done correctly. So for example, if I wanted to, if I computed the number of prime numbers between 1 billion and 2 billion, if I told you that between 1 billion and 2 billion, there's 61,010,004 prime numbers. There aren't actually, with high probability. But then, like, if I just told you that, then like you wouldn't necessarily believe me, right? But what I could do is you could basically make this cryptographic proof where I run the computation of just like going between 1 billion and 2 billion, checking every single number to see if it's prime, adding up like how many numbers actually are prime. And I could run this really, really long computation, and I could give you the answer along with a cryptographic proof, and you can just verify the cryptographic proof without having to do the entire computation yourself, and you would be convinced of like how many prime numbers there are between 1 billion and 2 billion. Now, nobody cares how many prime numbers there are between 1 billion and 2 billion, but there's a lot of kind of much more useful computations that you can use general purpose zero-knowledge proofs for, and one of them is, well, you can use them to verify blocks. So basically, the really long-term vision here, right, is that you just use general purpose zero-knowledge proofs to kind of completely verify everything about a block. So you just add a cryptographic proof that shows that a block is kind of completely correct, that everything was computed correctly, that every transaction is valid, that every transaction did what it's supposed to do, and then you can just download some data, check the proofs, and you can kind of very quickly verify the chain without actually running everything yourself, right? So this is kind of the 10-year dream. And like there are projects that are like Coda, for example, that's trying to do this for kind of a much more restricted kind of blockchain right now. But the problem is that the technology is not really ready for zero-knowledge proving kind of arbitrary general-purpose computation, right? There's just a bunch of reasons why it's complicated and it's extremely inefficient and so forth. But what zero-knowledge proofs are already really good for is structured computation, right? So computation that kind of has a pattern that just says, it's repeating the exact same step over and over again. And so it is possible that you can just basically verify that a piece of data has been erasure coded and kind of hashed correctly, and that some piece of data actually is the Merkle root. So basically, you just make a Stark that proves that this, where is it? You make a Stark that proves that this R prime actually is the Merkle root of an extended version of a piece of data, and you just publish this, right, along with the Merkle root. And then if someone downloads this Merkle root and they download this proof, then they know for a fact that the proof represents, or that the root represents a piece of data that has been encoded correctly. And so if you have that proof, then you can do the, sorry, latency. This, no, this thing is violating my synchrony assumption. So the, basically a client can just randomly sample, randomly kind of verify that with very high probability more than half of the data is available. And if they have that, then basically what they know is that because more than half the data is available, if there is even a single honest node verifying all of the data, then that honest node can download more than half of the data, use it to reconstruct the whole thing, and it will be correctly, the data will be correctly formatted, right? So if you use Starks to verify correctness of extended Merkle roots, then you do not need fraud proofs, right? And this is a general kind of pattern that zero-knowledge proofs and fraud proofs are kind of in competition with each other. And we've seen this already, right? So like, for example, there's ZK rollup, which is a scaling solution based on zero-knowledge proofs. And then there's optimistic rollup, which is a scaling solution based on fraud proofs. And I mean, a couple of days ago, there was a bit of a Twitter war where a ZK rollup person was kind of arguing that fraud proofs are, or that the security assumptions behind fraud proofs are a really big problem. The two technologies are definitely kind of competitive with each other. And they have different trade-offs, right? So the optimistic approach for the fraud-proof-based approach is good because it's kind of easier to implement, more general purpose, and it's, I would say it's cheaper. But the zero-knowledge proof-based approach gives you this kind of tight level of security without having to rely on network assumptions, right? So there's like, even if the network is unexpectedly really slow, like even if the network is unexpectedly extremely slow, like even if the internet, like the two halves of the world get cut off from each other completely for 4 days, it's not going to break zero-knowledge proofs. And so the technologies do have these kind of different trade-offs to them. And I would argue that because of how kind of nicely structured the computation around of Merkle roots is, like, look, it's structured. Like, do you agree that this is structured? Okay. Then, like, Starks are actually a pretty good fit for this, right? So if you have Starks, then you can basically you can get the benefits of kind of fraud-proof based validation. Now, there's a kind of new idea here, which is basically that you could create an architecture for a sharded chain where kind of at consensus layer, you verify correctness of the beacon chain, you verify availability and validity of the beacon chain, but you only verify availability of the shard chains, and then you use the beacon chain like kind of internally to detect when blocks in shard chains are contain incorrect computation, and if they do contain incorrect computation, then instead of throwing away the entire beacon chain and like breaking Casper and kind of the messiness of that, you just kind of correct faults that happen inside of the beacon chain. So this is real, basically what this does is it prevents high network latency from kind of reverting finality, and it makes the security assumption more subjective, right? So you personally, depending on like what you think is the risk of network, like what network latency is likely to be, you can choose how long you're willing to wait for a fraud proof. And if you want to verify that some computation in a shard happens correctly, But for availability, we use basically Starks and with the random sampling, and Starks and random sampling do not depend on fraud proofs. And so if there is high network latency, that doesn't compromise the basic integrity of the chain. So this is kind of one of the kind of idea for improving the kind of security model and the story of what would happen in the Ethereum chain if there was a 51% attack, or for whatever reason a committee were to get attacked, right? So there's two I guess to kind of summarize, right? There's two use cases for these technologies, right? So data availability for proofs and fraud proofs are really nicely complementary, because fraud proofs basically say if there's a bunch of data and you know the data is there and there is computations, then you can, instead of running all the computations themselves, just run a bit of computation, and you can wait for fraud proofs. And if nobody submits a fraud proof, you know the computation's correct. And data availability proofs let you verify that data actually is correct, or sorry, data actually is available. So data availability proofs catch the case where data is not published. Fraud proofs catch the case where data is published, but there's something incorrect about the data. And these two technologies kind of combine in this really powerful way to enable scalable validation that is 51% attack resistant. And so basically it reduces the power of a 51% attack to the point where, just like in current non-scalable blockchains, the only thing a 51% attack can do is it can reverse transactions. It cannot, with if everyone uses fraud proofs and data availability proofs, a 51% attack cannot force invalid blocks through. It can only revert. So two use cases. One use case, and this is a use case that could theoretically be developed now, is verifying existing chains, right? So basically, imagine you have a big long chain. It could be the Bitcoin chain, it could be the Ethereum chain, it could be the Bitcoin Satoshi's Vision chain, it could be whatever chain. And it has a lot of data. The more data, the better. So what you do is you connect your node and you ask the network, please give me a Merkle root of an Erasure code extended version of the entire chain, the entire big hulking file. And whoever provides the Merkle root, they can also provide either a proof of work to show that they're serious and they're not trying to DOS you, or a signature from an account that has some coins in a smart contract. And so if they commit fraud, then a fraud proof can be used to penalize them and take their deposit away. So take the blockchain, serialize, Merkleize, you have the Merkle root. Then now that you have the Merkle root, you randomly sample for some branches, you do your data availability challenges, verify that enough data is available to recover the entire data, and then you just go ask the network for fraud proof. You send out some messages that say, hey guys, I think this little hash over here is a Merkle root. Please tell me if you know about any fraud proofs. And you wait a long time for fraud proofs, and if you see no fraud proofs, then you accept the chain as valid. Right? So basically with this kind of architecture, you can kind of augment existing syncing processes and even existing light clients to give a security guarantee that's much closer to full validation. Use case number 2 is scalable blockchains, right? So in Ethereum 2, when your node receives a kind of a beacon chain block, and that beacon chain block contains shard data, Merkle roots of shard data, basically instead of downloading the entire thing, you can perform data availability checks and you can perform fraud checks. So in both of these cases, right, kind of quick validation of existing blockchains and scalable blockchains, we can kind of change the security model and make it one that's kind of gives considerably stronger guarantees to clients. You could also use this for plasma chains. So, conclusion: this is good. This is good for scalability, and this is good for improving security guarantees. And Starks can be used to make all of this stuff even better. Thank you.
Thank you very much. Would you like to do some QA section?
Okay.
Do we have any questions from the audience? If you have any questions, please raise your hand. Anyone? Any questions? Okay, we do have a question over there.
Yay.
Can you use snarks to make it better?
You can, yeah. I guess the reason why there's two reasons why I didn't say snarks. One of the reasons why is because snarks have like trusted setup assumptions, and especially like trusted setup assumptions are evil at layer 1. But like, if you're doing a layer 2 thing, it could be fine. Another reason is that this scheme is really bottlenecked at proof generation level. And so basically we're talking about doing proofs over hashes of many megabytes of data. And when I did when we did the math, it seemed like one of these proofs for like even a single ETH2 block would take a few minutes to generate. So like this is the sort of thing that already would basically require like at least somebody to run a GPU farm. And snarks like make that even more extreme because everything other than snarks takes longer to generate proofs for because you have to like do elliptic curve stuff or whatever instead of just an FFT. And the third reason is that for data availability checking specifically, you're already doing about 100 kilobytes worth of checking Merkle branches, so an extra 100 kilobytes for a snark is not going to kill you. So I think like you can absolutely use a snark, but I feel like snarks are like in this particular case a better fit.
Great, thank you. Do you have any more? Yes, we do have one more question from the audience. Yes, rolling over to Ethereum 2, like moving the Ethereum 1 system into Ethereum 2, well, 2.0 will require, I mean, the actual I wrote an ETH research post about how the transition will work. I think if you just go on ETH research and you check, there's something called ETH1 to ETH2 transition. It's not technically a hard fork, but it is a kind of moving of the state from the proof of work chain over to the proof of stake chain. But there will be hard forks required before this to kind of prepare the ETH1 chain for this for the transition. Great, thank you very much. We have one last question. Do we have anybody for the one last question? Yes. Okay, the question is what makes you wake in the middle of the night? Sharded peer-to-peer networking. Does that answer your question? I guess so. Okay, great. Let's give a round of applause for our keynote speakers.